Okay, in this class I'm going to continue our work on conditional probability and look at another example. Remember, we've derived this formula for conditional probability in previous classes. Make sure you are up to date on all that. So we're just looking at an example here. It says the probability of A union B is equal to 0.7. Remember always that just means in A or B. And the probability of A is 0.5. And the probability of A given B is 0.6. So generally that word given is written in there for that vertical line. So the probability of A union B is 0.7, the probability of A is 0.5, and the probability of A given B is 0.6. We're asked to complete a contingency table, a Venn diagram, and evaluate the probability of B. Okay, so what we're going to do, we're going to start off with the contingency table and put in what we can. And there's not all the information here necessary. So if this is row A, well, this has to be row A complement, and that is the total sum. If this is column B, well, this has to be column B complement, and this is the total sum. And we're going to put in probabilities. So the first thing, if I look at this first piece of information, the probability of A union B is 0.7. Well, where can I put that? There's no cell actually for A union B, but this cell here, A complement intersection B complement, that is the complement of A union B. Now remember, we said before that the probability of any event added to the probability of its complement has to be equal to 1. Well, the probability that something is in set A or B, well, the complement of that is that it is not in A and not in B. It's in neither A nor B. Neither nor is the complement of either or. So this cell has to add to 0.7 to give me 1. That has to be 0.3. The other thing, of course, I probably should have started with is that the sum of all probabilities in my contingency table has to be 1. The second piece of information here I'm going to look at is the probability of A is 0.5. That's that cell there. So the probability of A complement also has to be 0.5. Why? Because together they have to combine to give me 1. Working out here, that means this must be 0.2, since it's the number I add to 0.3 to get 0.5. We're also given that the probability of A given B is 0.6. That is not a cell in my table, so I might just think about this for a moment. The probability of A given B is 0.6, and we have a formula that we generally use when we're dealing with conditional probability. The probability of A intersection, or A given B, is the probability of A intersection B divided by the probability here on the condition, which is B. And that's 0.6. So what can I do here? Well, I can solve for one of these probabilities in terms of the other to give me a kind of a relationship between the probability of A intersection B and the probability of B. So multiplying on both sides by the probability of B will give me the probability of A intersection B is equal to 0.6 multiplied by the probability of B. Now suppose I just let the probability of B be equal to X. So the probability of B is equal to X. This is telling me the probability of the intersection will be 0.6 times X. And what I have here is, a way to establish something. I can establish something here. We know this is 0.2 times X. Sorry, 0.6 times X. And we know that if we add 0.6x to 0.2, we have to get X. So 0.6x plus 0.2 must give me X. So I'm going to solve here for X. I'm going to start by subtracting 0.6x from both sides, which will tell me 0.2 is equal to 0.4x. And then I'm going to divide on both sides by 0.4. So I'm going to get 0.2 divided by 0.4, and that's equal to x. Therefore, x is equal to, or 0.2 over 0.4, that's the same as 2 over 4, or 1 over 2, or a half. X is equal to 0.5. So x is equal to 0.5. From here, now I can complete the contingency table. It was incomplete initially because I didn't have enough information, but I was able to define a variable and solve. So I'm going to rewrite my contingency table with all the information in. I'm going to draw a Venn diagram, and I'm going to evaluate the probability of B. So let me scroll down the page a little bit. So my Venn diagram, so my completed contingency table is going to look like this. We have events A complement, and then the sum of those events, we have the events B and B complement, and adding everything up. So put in all the original things we had in. We had 0.5, we knew that was 1, we knew that was 0.3. We're able to work out everything else. So we're able to work out this had to be 0.5, so this had to be 0.2. From there, we were able to find a value for x. X in this case is 0.5. Okay, and from here we can, figure out everything. 0.5 adds to 0.5 to give me 1. 0.3 has to add to 0.2 to give me 0.5. And 0.2 has to add to 0.3 to give me 0.5. There's my completed contingency table. What would my corresponding Venn diagram look like? Well, we have a big box for the universal set. We have a couple of loops in here, A and B. The intersection here is 0.3. Out here is the complement of the union. That corresponds to that cell, 0.3. And then we've got in A but not B, in A but not B, that's 0.2. And then finally in B but not in A, we're in column B but not in row A, that's 0.2 also. All of those probabilities have to add up to 1. Okay? And the last thing we were asked to find in the question was find the probability of B. That's what we were looking for. So what is the probability of B? Well, the probability of B was exactly what we said x would be. So the probability of B, that's all the probabilities from column B, that's 0.5. Okay. Contingency tables, Venn diagrams, it can all be done without them, but they're really useful tools. What starts out off as, I suppose, a tricky enough probability question with some basic tools, contingency tables, defining a variable, solving an equation, becomes actually quite simple. Okay? So keep practicing. We're in section 5.7 in your textbooks. So keep practicing. Contingency tables, useful tool. Venn diagram, useful tool.